Let's talk now about invertibility of time series models. And we're going to look at this through a specific example using an MA1. Actually, we'll be looking at a couple of examples, but first we're going to show that we're going to parameterize this MA1 model as xt equals at minus theta 1, at minus 1. And so our example here will be xt, or actually our first example will be minus xt equals at minus 0.5 at minus 1, where that's an MA1 with theta 1 equals 0.5. So this particular video is going to look at specifically how to determine if a time series model is invertible or not. Later we'll look at the advantages of invertibility and the disadvantages of non-invertibility. But just to determine if a model is invertible or not, all we have to do is look at the characteristic equation, the roots of the characteristic equation of the MA side. And it's very similar to what we did for stationarity, where we looked at the roots of the characteristic equation on the AR side. And if those roots were outside the unit circle, it was stationary. If they were on or inside the unit circle, they were non-stationary. It was a non-stationary model. Same idea with the invertibility. We just look at the characteristic equation of the MA side like we're about to do right now. If those roots are outside the unit circle, then it's invertible. If it's on or inside the unit circle, then that model would be non-invertible. So this is a fun little game. We say xt equals, and we put it into backshift notation, like so. Awesome. And then we say, hey, that right there is the information we need to know about invertibility. And so we'll turn that into a characteristic polynomial. 1 minus 0.5z equals 0. And we'll note that this is minus 0.5z equals negative 1. And so that's z equals negative 1 over negative 0.5. And that turns into z equals 2. And clearly 2 is outside the unit circle. It is greater than 1 in absolute value. And so we know that this is an invertible model. Now, let's look at another example. This time we'll have xt equals at minus 2 at minus 1. And we'll check to see if this is an invertible time series model. And so that would be very simple. All we do is say xt equals 1 minus 2b at, and say, okay, we've got all the information we need about invertibility right here. This is 1 minus 2z as the characteristic polynomial equals 0. And we've got minus 2z equals negative 1. So z equals negative 1 over negative 2. And thus the root, which is z, is equal to 0.5, which is less than 1 in absolute value, is inside the unit circle, and thus this would be a non-invertible model. And so these are the two examples we're going to look at kind of going forward when we talk about the advantages and disadvantages of invertibility, which we'll talk about next. So great job. See you in the next one. Let's talk now about invertibility and how it relates to model multiplicity. And to define model multiplicity, it is simply two models that have the same correlation structure. And by correlation structure, we mean two models that have the same autocorrelations for every lag. So what we're going to do is kind of demonstrate this idea with an MA1. It's going to be very easy to kind of show this with an MA1. Now I've got two examples here of two MA1 models. One with theta 1 of 0.5 and one with theta 1 of 2. And so what we have here is, again, because it's simple to work with an MA1, this is the correlation structure of an MA1, where we know that rho naught is always equal to 1. We know that rho 1 for an MA1 is negative theta 1 divided by 1 plus theta 1 squared. And rho 2 for all of the rho 2, rho 3, rho 4 to rho infinity would be equal to 0, which is a unique, very interesting property of an MA model. So awesome. Let's go ahead and check out what the correlation structure is for this MA1 here that we know is invertible. This is an invertible MA1. Roots are outside the unit circle, but let's check it out. So this is rho naught equals 1, because it always does, and rho 1 equals, and now we've got, this is negative 0.5 because theta 1 here is 0.5, divided by 1 plus 0.5 squared. Looks good, and that is equal to negative 0.5 divided by 1 plus 0.25, which equals negative 0.5 divided by 1.25, which is equal to negative 0.4. And then row 2 equals 0, and that goes on forever. Great. Okay, so we're going to look there at the correlation structure of this MA1. Now let's look at the correlation structure of this MA1. We'll have rho naught equals 1, okay? We've got rho 1 equals, now that's negative 2, because theta 1 here is 2. Negative 2 divided by 1 plus 2 squared, which is equal to negative 2 divided by 1 plus 4, which is 5, which of course equals, just put it down here, rho 1 equals negative 0.4. And of course we have here that rho 2 is equal to 0 because it's an MA1, and that goes on for row 3, 4, 5, 6, 7, and forever. So we've got two models here that have the exact same correlation structure, and that is what we mean by model multiplicity, and that is not a good quality to have. It's not a desirable quality to have. When we've got a time series model, if we have two unique correlation structures, we'd like for those to be associated with two unique models. This one here, of course, being non-invertible, this one invertible, and theory will tell us that this is the only invertible model that has this correlation structure. Whereas there could be many non-invertible models that have this same exact correlation structure. So great, that's what we mean by model multiplicity. The big takeaway here is that invertible models, if you have an invertible model, you can rest assured that it has a unique correlation structure. Great job, see you in the next one. Now let's look at the second implication of invertible models, and that is if we have an invertible model, we know that the present is related to the past in a sensible manner. And if we do not have an invertible model, that is if we have a non-invertible model, then the present is not related to the past in a sensible manner, and clearly we would like the present to be related to the past in a sensible manner because we're sensible people. However, what the heck does that mean? What does it mean for the present to be related to the past in a sensible manner? Let's check it out and look at some examples once again. So here we have our MA1. Again, we'll demo this with an MA1. And we see this relationship. Let's just looking at an MA1, it's XT is related in some way to the residual in the past and then some random noise. So what I'm going to do is rewrite this relationship and kind of just note it over here that we will have AT. If this is the case, then AT is equal to, right? And then that would be XT plus theta 1 AT minus 1. Right? If this is the relationship, the equality sign, I just take this piece and stick it over there, just add theta 1 AT minus 1 to both sides, and I have this relationship between AT, the noise, XT, and AT minus 1. So if that's the case, then this is just saying that today's noise is related to today's observation plus theta 1 times yesterday's residual, yesterday's noise. So if that's the case, then what about yesterday? What about yesterday's noise? So yesterday's AT minus 1, or AT minus 1 from yesterday, will be, that's a T, then this will be yesterday's observation plus theta 1 times 2 days ago's residual. Right? It's just the same relationship, we're just scooting it back a day. So what about 2 days ago? So 2 days ago's residual is equal to XT minus 2, yesterday's, or 2 days ago's observation, plus theta 1 times 3 days ago's residual. And let's just keep going, right? Just getting the rhythm here. AT minus 3, if this is the case, if this is a relationship between today and yesterday, then AT minus 3 will equal to XT minus 3 plus theta 1 AT minus 4, and why not? One more time, just to make sure we have it. get in the rhythm. That is at minus 4 equals xt minus 4 plus theta 1 at minus 5. Great. Okay, so what are we going to do with that? So what we're going to do with that is I'm going to rewrite this here just to make this, just because it will play out easier for us later, but it's an equality sign, and we've got this here. So what I'm going to do is write this as xt equals negative theta 1 at minus 1 plus at. All I'm doing here is just putting at at the end, just for convenience. So if that's what I have here, then what we'll see is that there's at minus 1 and there's at minus 1, and that's equal to this. So I'm just going to substitute this piece in for this. And when I do that, we're going to be really careful and go slow here and write small, because you need all this space. This would be xt equals negative theta 1 times at minus 1. But at minus 1 is xt minus 1 plus theta 1 at minus 2. Right? That's all that is in there for at minus 1 right there. Just that piece went into there, and that's what we got, plus at. And so if we rewrite that, we'll have xt equals negative theta 1 xt minus 1. Negative theta 1, distribute that. That'll be a negative theta 1 squared times at minus 2 plus at. And we've played our game once. Let's play it another couple of times, because now we have at minus 2. And that's why I wrote this one. That's at minus 2. So check that out. I'm just going to plug that in right there for at minus 2 and see what we get. So that'll be xt equals negative theta 1 xt minus 1, yesterday's observation, minus theta 1 squared times at minus 2, where at minus 2 is that piece. Boop, put it right in there. That's xt minus 2 plus theta 1 at minus 3, right? That just plugged into there, plus at. Great. So let's keep rolling. Xt equals negative theta 1 xt minus 1 minus theta 1 squared xt minus 2, and then distribute the negative as well. That's negative theta 1 cubed, going to be important later, cubed at minus 3 plus at. Okay, great. Let's do one more. So if we have xt equals negative theta 1 xt minus 1 minus theta 1 squared xt minus 2 minus theta 1 cubed, at minus 3, there's at minus 3. So I'm going to plug in that. That is xt minus 3, right? Xt minus 3 plus at minus theta 1 at minus 4 plus at. Great. So we will expand that. Xt equals negative theta 1 xt minus 1 minus theta 1 squared xt minus 2 theta 1 squared minus theta 1 cubed xt minus 3 minus, distribute the negative theta 1 cubed. That'll be theta 1 to the 4th at minus 4 plus at. And now we're in a position to look at what's going on here, because we've seen enough of it. So we can see that these are the observations. This is today, and this is the past, right? That's t, and that's xt, and that's xt minus 1, xt minus 2, xt minus 3. That's at minus 4, but at minus 4 in our next iteration, we'll be plugging this into there, and we'll end up with negative theta 1 to the 4th times xt minus 4, minus theta 1 to the 5th, at minus 5, so on and so forth. But what does that mean, right? Recall that when we have an invertible model, All right, we're just going to play a little mental exercise here. Invertible model. That was, let's say we had xt equal, just as for example, we'll write it like this. That was minus 0.5 at minus 1 plus at. And what will that do? Well, when we see that, let's see here. When we write this out, when we have an MA1, then we can say xt equals, and then so just recall here, we'll have, just remind us that theta 1 equals 0.5. And so when we plug 0.5 into here, we'll see that xt equals this expression. So I'll have xt equals this piece, but this is equal to that, which is negative 0.5 xt minus 1, right, minus 0.5 squared, which is 0.25 xt minus 2, minus 0.5 cubed, which is 0.125 xt minus 3. And then this will keep going, minus theta 1 to the fourth, which is 0.5 to the fourth, which is 0.0625. And these coefficients will keep getting smaller and smaller and smaller. So I'll just say kind of dot, dot, dot. And so that's showing that the present is related to the past in a sensible manner. It makes sense to us that the farther away we get from today, the less that will have, the less influence that will have. These coefficients are approaching 0, as you can see here. So now let's look at one where the present may not be related to the past in a sensible manner, and we'll look at a non-invertible model. In fact, in this case, the present will not be related to the past in a sensible manner. So this will be non-invertible. We'll squeak it in here. This will be, let's say we've got xt equals one that we're familiar with, negative 2 at minus 1 plus at, where we see here that theta 1 equals 2. Right? So if I have that model, that's an MA1 with theta 1 equals 2. We know that it's non-invertible. The roots are inside the unit circle. So let's see what happens. Let's see what that means. And this is xt equals, so here we've got minus 2, no problem yet, minus 2 xt minus 1. So today is equal to negative 2 times whatever yesterday was, minus theta 1 squared. Okay, so that'll be 4 times xt minus 2, minus, okay, 2 cubed 8 xt minus 3. And that'll just keep on going. The next one will be 16. The next one after that will be 32. And if I go out, so if I go out to a trillion, so today, a trillion days or a trillion time units ago, the coefficient of that will be 2 to the trillion, x to the t minus a trillion. And that's just not sensible. That's saying if we go really, really, really far back, it really drowns out anything that happened in the more recent future, at any time in the future, in this particular model, in a non-invertible model. So that to be said, a quick caveat here, it doesn't mean that this has to be monotonically decreasing towards 0, right? It's just saying in the limit, as we go as far out as we want to go, this one will keep having increasing magnitude. The absolute value of those coefficients will diverge from 0, will keep increasing, whereas here, as we approach 0, those coefficients will also approach 0. And that is a sensible relationship between the present and the past. In invertible models, we have that relationship, and in non-invertible models, we don't have that relationship. So great, that's a quick and thorough primer on invertible models. Recall that you have to look at the MA side. That's a really important part. To determine invertibility, we're looking at the MA side, the characteristic equation of the MA side of the time series model, whereas for stationarity, we're looking at the AR characteristic equation, looking at those roots. So great job, keep it up. Isn't this stuff a blast? I'll see you in the next one, and we'll keep it rocking.